along B is 0. No, it's not necessarily. The conductivity of a material is due to a couple of things. One is, what is it? The mobility of the charge carriers is one thing, which is very high in a plasma. But the density of those charges is another one. And in a cosmic plasma, the density ain't that great. You know, so many per cubic meter. So the conductivity is not necessarily infinite, and the E field is often not 0. The frozen-in idea is wrong. I'll talk about that in a minute. And these ideas of a double layer, I haven't really mentioned what a double layer is, but a double layer is a wall that separates two cells of plasma, much like the cellular wall would separate blood cells. And if you ignore Perat's instabilities, you're going to get the wrong answer. And there's several other things. The first one is one of the things that sort of I worry about all the time, and that is that you only write magnetic field line pictures and never worry about the currents that actually create those magnetic fields. I claim that you will make progress if you think about the currents as well as the fields that they produce. And this last one, of course, is the magnetic reconnection idea, which I'll hopefully get to. This is, just briefly, what is a double layer? If you have 2 points, let's say A and B in a plasma, and they're at radically different voltages, the plasma doesn't like that. But the plasma generally cannot vary the voltage linearly between point A and point B. What you'll see if you use your Langmuir probe is you go from point A, and if point B is at a lower voltage, you'll get lower and slightly lower as you get away from A. And all of a sudden, whoop, the thing will drop almost to the voltage of B, and then it'll stay pretty much at the voltage of B. In other words, the transition in voltage happens in a very narrow range of distance. That's a double layer. And what you see here is a sort of a stylized one-dimensional double layer. Clearly, the top one is there's a voltage of, let's say, point A, which is high, and a voltage at point B, which is low. And so that obviously, by definition, the electric field is what? The negative of the gradient of the voltage of the scalar field, right? So if you plot the slope of this upper curve and then turn it upside down, that's how you get this. So clearly, that's why particles, charged particles, are accelerated in a double layer. It's like a pebble on a slippery hill. You slide down that hill. The force on the positive charge that's doing the sliding is maximum right in the middle. So the E field is highest, the force per unit charge to push it to the right. That's just by definition. Now, what about this bottom layer? Well, another one of Maxwell's equations is that the divergence of E is proportional to the divergence of epsilon E, the permittivity times the E, is equal to the charge density. The divergence relationship in a one-dimensional deal like this, it just turns out to be the simple derivative with respect to distance. So if you take the derivative of this curve, i.e. plot the slope of this curve, you get this curve. You can see that the slope in here is it's a maximum right there. The slope at the top is flat, so it's 0, so the slope is... Okay, so what this means, in order to get that voltage picture, which gives you, of course, by definition, that force picture, requires a double layer of charge. Now, what keeps the double layers from slamming together? That's like a capacitor with plus and minus charges. Why doesn't it just slam together? And the answer is that's the reason Irving Langmuir got the Nobel Prize. He figured out why that doesn't happen. It doesn't happen because it's a dynamic kind of a thing, not an electrostatic kind of a thing. And it requires a certain number of plus charges going one way and a certain number of electrons going the other. And this can become extremely stable. It also can very abruptly become unstable and disappear. In which case, it's just like opening the switch in a transmission line. That if the double layer, which is conducting current, disappears, explodes, that's what Alfvén saw in those power lines in Sweden, you'll get a the disruption in the current. These, we believe that these double layers happen all over the place and can have tremendous voltages. Of course, the galactic business is all supposition, speculative. So is the solar one. But it appears that there may well indeed be a double layer associated with the surface of the sun that occurs somewhere in the neighborhood of the chromosphere, above the photosphere, which would be responsible for accelerating positive ions down that potential hill outward. It also has the potential, to use a pun, to explain the solar temperature minimum. The idea of a smooth laminar flow of ions and then sort of white water at the bottom. So I don't want to get into that because that's all speculative, and I'd like to stay with what we really know. So there's my hero, Hannes Alfvén. He did so many things that it would take me all day to tell you how many things he did. He's obviously the father of plasma cosmology. He, in 1940-something, 41, suggested that there could be longitudinal waves in plasma, as well as the transverse electromagnetic ones. And he was laughed at. Oh, that's impossible. It can't be. And so one day, and I think it was 1942, at a convention, a meeting, scientific meeting in Chicago, he was expounding on these so-called waves in plasma. And it happened that Enrico Fermi was in the audience. And so Alfvén's babbling along about how great these things are and what he can do with them and so on. And all of a sudden, Fermi begins to nod. And the story goes, Fermi was heard to whisper, yes, this can happen. Yes. And all of a sudden, all the audience is going. And so Alfvén waves were accepted. They were also actually verified in the laboratory, about a year later, something like that. I talked about the explosive release of energy. He's also credited for the idea of CIV, which is the critical ionization velocity. The question, how do you get charge separation in space? Answer, you have a plasma and you have a neutral gas cloud approaching each other with relative high mutual velocity, relative velocity. If the kinetic energy of the neutral particles, 1/2 mv squared, is higher than the ionization potential, the neutral gas becomes ionized. It's been verified over and over and over. He was also a bear about this idea of magnetic fields not being frozen into plasma. And the reason he was is because he was the guy who came up with the idea in the first place. He knew Maxwell's equations. And it was only that he came of late to the idea that there had to be some little tiny electric field, and therefore magnetic fields are not frozen in plasma. It's a good thing they're not, too, because the only way you generate current is by relative motion between a conductor and a magnetic field. That's what keeps the lights on in this room. And the plasma is the conductor part of that little operation. So if plasma is moving with respect to the magnetic field, you will generate a current in the plasma. And therefore, the current will generate the magnetic field. That's how the magnetic field gets there. He also said there's no such thing as magnetic reconnection. We'll talk a little bit more about that in a bit. And also the idea that there's no such thing as an open magnetic field line. You hear helioseismologists talk about the footprint on the sun from which the magnetic lines of force emanate, and then they go out to infinity like the skirt of a ballerina and all that. There's no such thing as an open magnetic field line, and I'll try to show why. There's a typical sketch of a magnetic field as shown in every physics textbook in the world. You put current in the direction of I there, put your thumb in the direction of the current, and your fingers will show you the direction of the flux. Also works if you put your fingers in the direction of the current, your thumb will be in the direction of the flux. So it works both ways. But the point is the magnetic field lines are a draftsman's artifice to show you where the magnetic field is strong. At the top, which is where the field lines leave, is the North Pole. And the magnetic field lines are very dense there, so it's a strong place. By the way, the arrows are a little bit misleading. There's nothing